Hello, this is Thursday's lecture for week 13. I'll be walking through the first part of Lab 10, so implementing the von Neumann architecture. So where we left off at the end of Lab 9 was we had this automated adding machine that could add or subtract an arbitrarily sized number just by keeping track of the carry out or the borrow and storing the intermediate results in our data RAM. What we're going to do today is address the problem: how do we go back and address a memory location that we've already passed with our program execution? For example, if we're on address 04 and we want to access some data that is stored at 01, we don't currently have a way to go back and look at things that are stored in previous memory addresses. The other thing that we don't currently have the ability to do is branch. So we can't write a program that makes a decision. For example, we can't write if-then statements because we don't have a way to branch to different parts of the code RAM depending on the consequences of an if-then. So there is a way to address that with this current architecture. This architecture that we're looking at now for Lab 9 is called the Harvard architecture. It's characterized by two different RAM arrays, one that holds the code and one that holds the data, and also one execution cycle. So right now, when we have a code, for example, load, store, add, subtract, add with carry, and so on, we just get that code from the code RAM and we execute that instruction right away. What we're going to next is the von Neumann array. Notice now we only have one RAM array that holds both our code and our data. The drawback is that we need a four-step execution cycle. We need one to get the instruction, to get the opcode. We're going to need two to get the high and low order address bytes, and the reason we need two is because we have 65,540 different addresses to look in, which means 256 or 8 bits or 256 unique addresses isn't going to be enough. We need 16 bits for 64K worth of addresses. So we're going to need two cycles just to get the memory address to go to. And then the last one is going to be to actually execute that instruction. That four-step execution cycle is known as the von Neumann bottleneck because now it's going to take 4 times longer, 4 times more clock cycles to execute a single instruction. So the drawback is it takes longer to execute, but one of the benefits is it's a little bit more efficient in resources because now you only have one RAM array instead of 2. And having said that, this Harvard architecture is something that's implemented even today in microcontrollers like you'll see in the ATmega for the Arduino, or the microcontrollers that you have in your car, your toaster, your washing machine, your laundry machine. So it's possible to make a fully functional computer. The only difference between a microcontroller and a computer is file storage and an input-output system with a Harvard architecture. It's just we're not going to kind of waste our time doing that because we're going to show how to do it with the von Neumann architecture. In other words, if you look at the last page of chapter 10, you'll see this is where we're going to. And the von Neumann architecture is what's used in the i7. So we started out with the 8080, which is the very first consumer available microprocessor. And that's the great-grandfather of the Pentium, which is the grandfather of the i7 that you probably have in your computers today. Those all use the von Neumann architecture, so a single RAM array that holds both code and data. Alright, so this is where we're going to. So let's just walk through the lab. First thing is we need to expand our instruction decoder for these new opcodes. All of our branching commands start with jump, and so we have 1, 2, 3, 4, 5 different things that we're going to need to add to our decoder. So let's just copy 5 of these, 1, 2, 3, 4, 5. Control C, Control V. These down here. Let's wire these together. Alright, now I just need to make sure that I've I think what I'm going to do off screen is I'm just going to change the name of all of these. I'll start with doing that. I'll be right back. Okay, I've just changed all of the names of these outputs to match these tables, all these 5 different commands. So now I've got to make sure my inputs match for the correct opcode. So for example, the first one's jump is 30. So I'm going to use the poke tool to make this 3, which is this, 30. So looking at the lime green inputs, I remember NOT gate is high only if all the inputs are low, so that means that this line and this line need to be inverted. So the third line on this NOR gate needs to be inverted. Looks like that worked. Then our next command is jump if 0, which is 3, 1. So 3, 1 looks like that. So it means this NOR gate needs to have the third line inverted. Looks like that works. Next one, jump if carry is 3, 2. 3, 2 is this. So I need to invert the fourth on this bit. Still not working. And the seventh. Good, looks like that works. And then jump if not 0 is 3, 3. 3, 3, add one more bit there. Means I need to invert the fourth and the seventh. Okay. And then lastly, jump if not carry is 3, 4. 3, 4 is that. Now I have to negate the fourth one and the sixth. And that doesn't need to be negated, so no. And that looks like that works. And you see how we've got some doubling here? I mean, sometimes this leads to problems, and so one way to heal that is you just pull it down. And you can push it back up if you want. Perfect. Okay. Now, okay, this looks a little messy, so what I'd like to do is take all of our jump commands and move them over to the other side. I'm looking in the lower right hand corner. Once I click this, I can see what NOR gate output it corresponds to. So that looks like that'll work. Alright, next we need to make a control unit subcircuit to institute our 4-step instruction cycle. So I'll right click on the main folder and add a circuit called the control unit. Alright, and first thing is we need a decoder. So if I look at plexers, I see I have a decoder and a demultiplexer. Like, what? You told me those were the same thing. Well, I should say Petzold told us those were the same thing. So remember when we were presenting this in class, we said the decoder, also known as a demultiplexer, is analogous to a train track switch. What it does is it determines where the train, what track the train is going to go. If the train is our data, we use these address bits to select which track to go to. And this was implemented in the Petzold text for the first time with the cat chooser. Remember, the one output is lit depending on what color cat you wanted. So this is fine when there's only one data bit, but if you have multiple data bits, then it makes more sense to call this a demultiplexer. When you take the value of this data and you transmit it to one of these outputs depending on which address you choose. And so Logisim will make a distinction between those two things. You notice a decoder, this one, only, we want a 2-bit decoder. Doesn't have an input. This thing tells us what address to select, but it doesn't have a data input, as opposed to a demultiplexer, which has a data input. So this will transmit the input data to one of these outputs depending on what address you select on this gray dot. And if you want to see what the pinout looks like, or you want a little more help on these, you can just go to the help file, and it tells you what each of these things does. For example, the south edge, right side indicated by the gray circle, is our select bits. Alright, so we don't want the demultiplexer, we want the decoder, and let's make this face north. Notice I use 2 bits because we have 0 through 3, 0, 1, 2, and 3. I need 2 bits in order to select that. And we also need a counter, which is under memory for some reason. Here I want a 2-bit counter to count from 0 to 3. And let's put a clock on that. You might be wondering, why am I using an input instead of a clock? Do you remember under wiring, I could use this, right? Then every time I hit the clock, it goes up or down. Why do that instead of actually having the input called a clock? Well, it's because we have to remember this is a sub-circuit of our main circuit. Our main circuit already has the clock in it. So we're going to use this clock output as an input to our sub-circuits, including, we did the same thing for the ALU if you remember. So it's a clock input, not the actual clock. And then we'll need a reset. And I know it's coming, so instead of just wiring it directly, I'm going to make a tunnel, because we're going to use the reset for a lot of the other chips here. I used Control-C and Control-V to copy the tunnel. And I recommend doing that because it's a way to make sure that you get the spelling and capitalization correct. Okay, what else does the lab say we need? Oh, these temporary flags to hold to keep track of what step we're on in the instruction fetch cycle. And let's execute instruction. Okay, I'm going to make 3 more flags off screen. Okay, I just added these 4 tunnels and made the names match what we have in the lab for each step of our instruction fetch cycle. And now let's wire these up. Alright, I think we have a sort of rudimentary control unit. Let's test it out. If I cycle my clock, I step through 4 different cycles. Perfect. Okay. Oh, it looks like we also need a data in with a tunnel, so I'll add that now. Remember to use the square for our inputs and the circles for the outputs. But our data input is an 8-bit input, which means this tunnel is going to have to take 8 bits. Okay, the reason why it's orange right now is because this has the same name, and so remember all the tunnels with the same names have the same characteristics, so we need to change this to data in, and I think that looks good. Alright, so next step is we need to have the data output of each of the code RAM array go to 3 8-bit latches. So it says to replace the first 3 tunnels with 3 8-bit registers and have the decoder output go to the clock for each register. So let's use Control A and slide this down just a little bit, because it might need more room. Alright, so registers under memory. Register. Eight-bit falling edge is very important. Okay, so instead of fetch opcode, so we'll call that the opcode register. Whoops. And this is our high order address byte register. last byte register. Great, and it looks like we're going to need our tunnels to go to each one of these places. So let's use the reset tunnel. You see, I'm a big fan of copy paste, and each of these has a data input. So let's send our data in tunnel. I don't know if you knew this, you can just hit the arrow key to change direction. So, shoot. Oh, I sent it to the enable instead of, I put it to the wrong place. There we go. Alright. Now what's next? Data in tunnel and reset port, that looks good. All are set to the falling edge, that looks good too. Now we need to make our shape. So this is what it looks like. Whoa. Oh, I forgot something important. Okay. The output of the opcode register needs to go to our instruction decoder. So let's put our instruction decoder in there. First I need to slide this down a little bit. Oh, you know what? I can gain some room here. Alright, I want to put our instruction decoder in, which is here. I want to face it north, I think. Yeah, I think that'll work. Okay, now these we need to label all of these outputs, because now these outputs are going to be the outputs of our new subcircuit. So here I'll do one. I'll record one and then I'll go off screen for the others. So output is the circle. And by hovering over this, you can see that it says load, so I'll change that name to load. And I'm going to do the same thing for all the other outputs. So I'll be right back. Okay, I finished labeling all the outputs of my instruction decoder, and just a reminder, I hover over each of these outputs and it tells me how to label each of these output pins. Alright, now the last thing I think we need to do is change our shape. And if you look at the last page of the lab, you'll see that this is eventually how we're going to wire it. And you don't have to wire it in this way, but I just found that it was convenient to have the load, store, add, subtract, add with carry, subtract with borrow all on the right, because those go to the ALU, and then all of our jump commands, we're not currently using these two for this part of the lab, go to the program counter, because those are going to tell us what address to jump to. So all the jumps on the left, the add and subtract commands on the right. So and it looks like my clock's over here, resets here, and data ends over there. So let's change this shape to sort of match that. Be a little bigger. I don't know yet how big. Alright, now you see when I click on these, there's a little picture that appears in the lower right hand corner that tells me what that corresponds to. And I could go back and forth between these pictures to figure out what that is, but that gets tiring. So I can just use this Snagit to take a picture. Snagit's available on your computer too. It just comes preloaded with Windows. And right now I can just use that for reference. Okay, so where'd you go? So that's the slower one. That corresponds to load, and we want load to be on the far right, using looking at the picture. Here, I know it's a lot to bring in on the screen. Let's do this. Looking at the last page of your lab to show you what the picture should look like. Let's see if we can get all these windows. All right. Okay. So anyway, this was load. This one's store. This one's the third from the top. That's add. Fourth from the bottom is add with carry. So on the right, subtract. And subtract with borrow. This is our halt, and the halt looks like it's going to be all the way over there. Okay, this one is jump if not 0, and jump if not 0 is the second one. So that one. The second one down on the list is jump if not carry, which is over here. This one's the third one down, which is jump if carry. This is the second one from the bottom, jump if 0. And looks like jump. Move our clock symbol down here. Okay, now the outputs. That's our clock input, which is the left-hand side. That's our, what is that, reset. So it goes here. And finally our data in, which goes here. This is my clock symbol. Come on. Okay, great. So we got the shape. It looks more or less like what we want, and I think we'll be ready. Oh, we need the splitter with the address from instruction. So one more thing to do in our control unit. These two outputs, high order address byte and low order address byte, are going to go to our output. So we need a splitter, which is under wiring. Where are you? Fan out of 2, a bit width of 8, no, 16, not 15. Let's face it. No, we need to face the other way. And then to an output pin, which is 16 bits wide. I think that might work. No, it's backwards. Okay. Do you see how high order address byte I put in a 1, 0, but that showed up at the bottom here. So that's not the way we want it. We want 8 through 15 to be on top and 0 through 7 to be on the bottom. So let's make that change in the splitter. See how it says bits 0 through 7 are on the top and 8 through 15 are on the bottom? We need to switch that around. So let's change all those to bottom. You can ignore the orange for the time being. We'll fix that in just a second. Now 8 through 15 need to be top. Okay, good. Now your lab asks you to make sure that you can load, that you can do a store, demonstrate that you can store a value at address 100A. So let's see if we can do that. First let me reset. So a store operation. I don't remember what store is. Store looks like it looks like that and that. So 1 is a store. So let's go to our control unit and put a 1 1. Our data in will be a 1 1. So when we leave this, when I hit this clock again, when it goes low and then high again, it's going to go to this next line, which means this is going to turn Kelly green. And remember, this updates on a falling edge. So this data in will be stored in this register once the instruction goes to the next cycle. That's great. Look, see, we got the we put the opcode of 1 1 in, and we got the instruction decoder said, yep, you want to store something. All right. Now our next goal is to put a 1 0 in the higher order address byte. So that looks like a 1 0. And if you want to be sure, it's sometimes useful to use these probes. Yes, 1 0. So we have 1 0 hex, and I want that to go higher order address byte. So when I leave that cycle, a 1 0 is stored in the top of the output. Perfect. Then we want to put a what is it, 0A? Yeah, 0A for the lower order address byte. So let's see, that 0 for that, and A is 10 in base 10, so that's an 8 and a 2. Okay, so we got that right, 0A. And now I want to, once I execute the instruction, that'll be saved in the low order address byte register. Yay! And just to make sure, let's add another probe. A. Nice. Okay, so it looks like we have a working control unit. We're done with parts 1 and 2 of the lab. Stay tuned. Next week on Tuesday we'll go over parts 3 and 4, and we'll be done with the von Neumann machine, and we'll start working on programming it. Okay, take care.